All right, folks, let's get started. Happy Friday. So we're going to continue on talking about geometry, all right, molecular geometry, because the whole idea in this chapter is that electrons are not dots on a page. They exist in 3 dimensions. So we looked at some examples here of Lewis structures and we predicted their geometry. So my method for predicting molecular geometry was up here. Yeah, okay. So first you always start with the Lewis structure and you focus on that central atom. We're only ever determining the geometry of just around one atom, all right? So if we have like a big complex molecule, we're not going to be using, you know, like tetrahedral, like trigonal plane. We're not using that kind of vocabulary if it's a really big complex molecule. We're just looking at simple things. All right, so once you have that Lewis structure, you count the number of electron domains around that central atom. So that includes bonds and lone pairs. So if you consider the bonds in the lone pairs, that gives you your electron domain geometry. That gives you the template where the electrons go, whether they're in bonds or in lone pairs. And so then the last step here is, okay, take into account any lone pairs that are on that central atom, and you literally cover them up. Because we see atoms, we don't see lone pair electrons. And so that's the shape that we communicate, what the shape the atoms actually make. And so oftentimes, students will forget this point that with lone pairs, we're literally just ignoring them. When you ignore them, I mean you just like cover them up. You don't let those bonds like spread out again. So you use the electron geometry as a template. So for example, we looked at ammonia here. Even though the Lewis structure looks like it's trigonal planar, like it looks like the molecule's flat because we drew it flat, the molecule actually doesn't adopt that shape because it has 4 electron domains. We start with our tetrahedral template and recognize, oh, but one of those electron domains is a lone pair. So you literally cover up that lone pair and think to yourself, okay, what shape does that make? That's trigonal pyramid, not planar. And that's a common mistake students see. Or in this case, we have ozone. There's 3 electron domains here. So you start with your electron geometry as trigonal planar, but because there's 1 lone pair and 2 bonds, we just see the bonds, we cover up that lone pair, and that gives us our bent shape. That's around 120 degrees. Versus something like water. Water will also give us a bent shape with those atoms, but a little bit differently here. If we count around the oxygen, there's 4 electron domains. That gives us our tetrahedral shape. But because there's 2 lone pairs, you cover up those 2 lone pairs. And so you see that we get another bent shape. But this bent shape is different. It's closer to 109 degrees because it comes from the parent structure, tetrahedral, and not trigonal planar like our ozone molecule. So there's a little detail there. All right, so the whole idea is, you know, electrons aren't dots on a page. We also want to think about the different requirements between bonds and lone pairs. That's on this next slide here. So if you haven't already, do memorize those electron geometry shapes. I guess go ahead and memorize the molecular geometry shapes, but I don't like to memorize those ones. I just think of the parent geometries and just start covering things up when considering lone pairs. So do practice that. All right, so, okay, that looks weird. Okay, so the next part of this chapter is we're just looking at small deviations from those ideal shapes that we discussed. So I said to memorize the shapes, so like octahedral, trigonal bipyramid, those names, but also memorize the bond angles of those ideal shapes. And what I mean ideal, that's if every electron domain spread out perfectly. In a tetrahedral, the bond angles would be 109.5. In a trigonal planar, it would be 120 degrees. So do memorize those numbers because what we'll see here is that actual molecules, sometimes they don't adopt the ideal shape. It'll deviate a little bit, but it's pretty easy to explain, understanding that the space requirements between lone pairs and the lone pairs and bonds. So let's think about it. So when we think about a covalent bond between 2 atoms. The electron density is basically between those 2 atom centers, the nuclei. Those electrons are attracted to both of those nuclei, versus something like a lone pair, all right, where, we have an X atom, there's like a lone pair on it, there's bonds or something. Those electrons have a larger space requirement. They just take up more space. I like to think, okay, lone pairs are larger than a covalent bond. They're just big and fluffy when those electrons are in a lone pair. And so what happens here is lone pairs take up just a tiny bit more space, and so it'll push bonds closer together that are in that molecule. So here's an example. Here's 3 molecules, CH4, NH3, and water. So here are the kind of the 3-dimensional Lewis structures, basically. But if you look at the central atom for all of them, they all have how many electron domains on all of them? 4. So all of them have the electron domain geometry of tetrahedral. But do they all have the same molecular geometry? No, because there's different number of lone pairs. So because all of them have the same electron geometry, they all use the same template. They all have bonds that are 109.5 degrees away from one another. That's the tetrahedral bond angles. But when we actually measure the bond angles in these molecules, we see that they're a little bit different than our 109 number that we typically think about with tetrahedral. So if you measure the bond angles in methane, you would in fact measure 109.5. But if you measure the bond angle in NH3, all right, it's still a tetrahedral electron geometry. You don't measure 109.5. You measure something closer to 107. Versus water, still an electron domain of 4, but we measure a bond angle around 104 instead of the 109.5. And the reasoning is because we have a lone pair that's present. Just think of this lone pair as this big, juicy electron that takes up a lot of room, and it pushes down other bonds a little bit closer together. Or in this case, for water, there's 2 lone pairs, so it's pushing those bonds a little bit closer together. And so that's what I say deviations from ideal bond lengths. But note that they're really, really close to the actual ideal bond length, all right? So that's the whole idea here. Lone pair usually decreases bond angles away from ideal, and just a tad, a little bit. And this is when we would actually measure it in like in an experiment or something. All right, so lone pairs mess up our geometry a little bit because lone pairs are big, fat, and take up a lot of room. Let's also think about the space requirements between a single bond and a double bond. Which one do you think takes up more room, a single bond or a double bond? Double bond. What's your reasoning there? There's more electrons. Yeah, a double bond has 4 electrons. A single bond has 2 electrons. So what we see here are deviations from our ideal bond angles when we have double bonds involved as well. So let's look at this molecule, all right? So just based upon that central carbon atom, what is the what's the geometry of that central carbon atom? Trigonal planar, because the electron geometry is 3. There's 0 lone pairs, so molecular geometry is 3, so it's trigonal. Yeah, it's trigonal planar. So what is the ideal bond angle, the one that you memorize? 120 degrees. All right, so remember what we said about space requirements between single and double bonds. So if we lived in an ideal world, yes, these bond angles would be 120 degrees because it's trigonal planar. But if we look at the actual details of this molecule and what we just said, that this double bond actually takes up a little bit more room. I'm gonna make it nice, big, and fat. All right, that double bond takes up more room there. Do you think these 2 carbon-chlorine bond angles, they'll be brought closer together because this double bond is taking up much, much more room? And so the idea here, what would be the reasonable bond angle for this bond angle right here? Exactly 120, more than 120, or less than 120? Less, yes. And again, all you have to think about is, oh, those electrons in the double bond just take up much more room, right? Versus, what if I didn't ask you this bond on that arrow? What about the bond angle right here on the red arrow? What would that be close to? Would it be more, less, or the same than 120? more than 120. And again, it's because where it is relative to the double bond, because the double bond pushes the other bonds closer together. All right, so see that really all in your mind. You just have to remember, oh, double bonds take up more room, lone pairs take up more room, so you'll deviate a little bit there. All right, quick question. Let's do this one actually. Okay, so let's do this one. All right. What about in nitrate? What do we think the O-N-O bond angles are in nitrate? A or B? What do we think? A. But I just said double bonds, so we think A, but I just said double bonds take up more room. So shouldn't some of the bonds be closer together? Yeah, so what's the trick here in nitrate? Nitrate is our molecule that undergoes resonance. Does that double bond actually exist in one place? No, it doesn't. That's why I drew 3 Lewis structures, okay? 3 Lewis structures. That double bond is actually everywhere in that molecule. It's kind of smeared around, so we don't see the same deviation we saw in the previous example. Because in the previous example, there's really only one place that double bond can be. There's no resonance structures, right? That this is a bond order of 2. Versus in nitrate, that double bond is smeared the whole way around, all right? So the answer here is precisely 120 because of resonance. If you have a molecule where you do have a double bond that's like localized, that it only exists in one place, we go through the thought process of, oh, you know, that double bond takes up more room. But in this example, it's a trick one. I tricked you. Or maybe I tricked you. I don't know. Or maybe you're really good when thinking about resonance. And again, nitrate is that example there. So when looking at nitrate and resonance, we talked about, you know, we're not going to see 2 long bonds and a short bond, right? We see 3 bond lengths that are all the same length. We also see 3 bond angles that are all the same length. And so that kind of points to the idea that, oh, there is not one correct Lewis structure for nitrate. All 3 of them are technically correct. And that's why this molecule undergoes resonance. And it's those measurements that, you know, tell us as chemists like what resonance is, this delocalization of that double bond. All right, so we see why it's not B. Okay, good. So hopefully you got tricked, okay? Hopefully you got tricked, because if you got tricked, then you learn from it, right? Okay, all right. So let's do some examples. Okay, let's estimate these bond angles. Okay, so 1, 2, and 3. So here's my strategy for bond angle. So remember, we're looking at the central atom. Yes, this molecule looks really complex, but all we're doing is focusing on the central atom. So for bond angle 1, we're looking at that oxygen. We're looking at the environment around that oxygen. And 2, we're looking at the carbon. And 2, we're looking at that other carbon. And note here how I draw the Lewis structure. I'm trying to trick you. I'm trying to trick you, right? I'm not drawing it how it actually looks like. We need to use our Vesper theory to figure out these bond angles. So my strategy here is you take a look at one at a time, each of those central atoms, and you go through Vesper theory, right? I already gave you the Lewis structure. So we want to predict the electron geometry, all right? The molecular geometry, or I guess, yeah, the electron geometry will tell us our ideal bond angles. Right? So this will tell us our ideal bond angles. Oh yeah, that's step 2, I guess. Then step 3 is you look at the actual structure after you've predicted your electron geometry and the angles, and think, okay, are there any deviations from those bond angles? And then that's how we would predict here. So let's look at bond angle 1. So ask ourselves, what is the electron domain number around oxygen? 4, and so 4 is what shape? Tetrahedral. Do you remember what the ideal bond angle is? 109.5. Great. So will that bond angle measure 109.5? No, because what's present? 2 lone pairs. So that bond angle will be more or less than 109.5. Less, yes, so less than 109.5. Because there's 2 lone pairs, I'm just going to say much less than 109.5. All right, next one. Bond angle 2. So this carbon, how many electron domains? 3. What shape is that? Trigonal, which one? Planar. Planar because there's 3. Trigonal planar. So what's the ideal in trigonal planar? 120. So then from that we think, okay, will there be any deviations from that number? Yes, because there's a double bond. And so think carefully here. Where is that arrow, the angle showing relative to the bond angle? Will that bond, make the our target bond angle closer together or slightly bigger? Slightly bigger, yeah, because it's showing this bond angle. If I was pointing to this bond angle right here, it would be slightly smaller. But in this case, it is slightly bigger than 120. Right? And then the last one, it's the same shape. It's electron geometry of 3, trigonal planar. So the ideal bond angle is 120 degrees. Will it be 120 degrees if you measured it? No. What will it be closer to? It'll be greater, right? Yeah, it'll be greater than 120 degrees. Okay. So deviations from our ideal bond angles is a really good type of question because it not only asks, molecular or electron geometry, it makes you think about the space requirements for single bonds versus lone pairs and double bonds. All right. So let's do this one. All right, one more. Which bond angle is closest to 109.5? 1, 2, or 3? So this is basically the same question, but I'm asking it a little bit differently, okay? Because the idea here is I give you the bond angle. So we need to think what shape is related to that number, 109.5. What shape? Yeah, tetrahedral. All right, so that means we are looking for the atom or the bond angle that adopts a tetrahedral shape. So 109.5 is a tetrahedral. So based upon that number, are there any deviations at play? If it's 109.5? No, there's not. So we want to look for the atom center that has a tetrahedral electron geometry and hopefully no deviations from that. So meaning no lone pairs or no double bonds here. All right. So for fun, why don't we just do all the bonds or all of the angles? So this carbon has how many electron domains? 4. So what shape is that? Tetrahedral. Is there any deviations? No, because it's all single bonds, so no deviation. So I think that the answer is 1. That's the answer? Yeah. But for fun, let's get all the bond angles, all right? So bond angle 2. What do we think that is? How many electron domains? 2. So what shape is that? Bent? No, it's linear. 2 dots always make a line. 2 dots always make a line. So it's linear. So now the question is, are there any deviations? Yes, but think about it. If we have 2 atoms that are already 180 degrees away from each other, right? That's the ideal bond angle for linear is 180 degrees. Does it matter if this side is big, fat, and fluffy? Is it going to deviate any more? Can it get any further away? No. So once you're at linear, you can't deviate anymore. Right? Because those electrons can't get any further away from one another. So bond angle 2 and 3 are about what value? They're going to basically be exactly 180 for both of them. So you won't see any deviations. You'll be correct in thinking, oh, there's a triple bond that should deviate, but think about it. Like once you have that big triple bond, that single bond can't get any further away if it's already 180 degrees, right? Okay, all right. So there you go. There we go. All right. So let's do some more. All right. So I wanted to go into more detail about some of the hypervalency electron geometries to kind of explain and keep in the back of your mind the space requirements for lone pairs. Remember, just think of them as big, fluffy electrons, all right? And they want to have a lot of room. So the idea here with our electron geometry of 5, trigonal bipyramid, meaning we have this like triangle belt, right? So that's where the trigonal part of the name comes from, and it's bipyramid because we have a bond sticking up to make one pyramid and we have a bond sticking down to make the other pyramid. So the interesting thing about this shape is that there's different bond angles to think about. There's this bond angle within the triangle part, that's 120 degrees, but then we also have the up and down part that are 90 degrees. So these differences of bond angles give us different space requirements, which will be important when we put on lone pairs if they're present in that molecule. So we call these different positions the axial positions, the ones that go up and down. That's your axis, like if you were spinning a top. And then the triangle belts region, we call the equatorial position. So like the equator, I guess if it was like a globe or something. I don't know. All right, so the equatorial positions, those are the 120 degrees, and then the up and down, our axial position, those ones are the 90 degrees. So the difference in positions, all right, of these two different regions. So we have the equatorial, the axial. When we put lone pairs on these shapes, remember, lone pairs will always go where it has the most space to spread out because lone pairs are big and fluffy. So the idea is that lone pairs will preferentially take the equatorial position because there's more room there. All right, so if you think about it, like just pretend if you were an electron, a lone pair, and you went in the axial position, let's just pretend, there would be 3 other bonds that are 90 degrees away from you. 90 degrees, all right? That's how the closest next bond. Versus if you were in the equatorial position, yeah, you have 2 bonds that are 90 degrees from you, but you also have 2 bonds that are 120 degrees from you. So if you're a big, fat, fluffy electron, where do you want to go? Where you're 90 degrees from something or 120 degrees from something? 120, yeah, so you're going to preferentially take the equatorial position. So that's how we get these different shapes when we start putting on lone pairs. You just want to think, okay, where does that big fluffy electron go? So if you have a molecule that just has 5 bonds on it, 0 lone pairs, you just have your parent geometry, trigonal pyramid, bipyramid. If you have 1 lone pair, remember that lone pair is going to go where it has the most room, so you're going to put one in the equatorial position. All right, so then you say the shape that's there of the atoms that are left, so you cover up that lone pair, and then you say what shape that is. That's a seesaw, when you take one of the positions away from the equatorial position. All right, so that's if there's 1 lone pair. So now the trouble is, now we want to put a second lone pair, but we still want to follow the same rules here. You want to put that lone pair where it's not bumping uglies with other things. So where will you put that lone pair so you get the most room? Will you put it on an axial position or will you put it in an equatorial position? Axial? So if you put a lone pair on this axial position, think about the angle that the 2 lone pairs make. If you put a lone pair right here, what angle is between this lone pair and that lone pair? 90 degrees. Versus if you put it in the equatorial position, what's the bond angle between those 2 lone pairs? 120. Yeah, and so that's why the next lone pair goes in the equatorial position, right? And then you cover up the lone pairs. What shape is left? What shape is left? It is T-shaped. Oh, it says right there, but I don't look at my slides. Okay, so there's that. Okay, what if there's 3 lone pairs? And again, so you just choose the spot where it gives you the most room, and so that would be the last equatorial position, and so what you see that is left of just the atoms is a linear arrangement. So if you don't place the electrons in the right place, just think of them as these big, fat, fluffy things. They want a lot of room, then you would get these shapes wrong. All right, so that's 5 electron domains. And so this is how we filled out that table at the very beginning of this chapter. I said to like memorize these shapes. That's where these shapes come from. It's from the idea when you start putting lone pairs on, you have to put that lone pair where it's given the most room to minimize repulsions with other bonds or other lone pairs. All right, so let's keep going. 6 electron domains. All right, so this is the last one, octahedral, but we still need to do the same thought process, okay? So octahedral, 6 electron domains. If we have 0 lone pairs, then the molecule is also octahedral, but we want to go through the same thought process of, okay, let's place on lone pairs sequentially to think where will they preferentially go. So this one's a little bit different. So with octahedral, all of these bonds on the parent structure are 90 degrees. So they're all equivalent. So if you put one lone pair on, just one on an octahedral, it doesn't matter where it goes because they're all identical places. So if you place a lone pair on an octahedral, what shape is left of the atoms? So if I made this a lone pair and then you cover it up and you say, okay, what's left? You have a square base, but it's a pyramid, so it's called square pyramid or square pyramidal or something like that. That's it. All right. So whether you choose, I chose the one that's facing south, the one in the basement to put the lone pair, but really you could choose anywhere. Okay. You could choose like this one. All right. You could choose that one. It's still square pyramidal. It's just you like rotated it. It's still the same molecule. Okay. All right. So the first one, right, is square pyramidal right there, right? That one. All right. So if you want to put another lone pair on, okay, so we have a lone pair in the basement. Where are you going to put the next lone pair? So it's furthest away from that first lone pair. You're going to put it upstairs. Yes. So do you see how we get the next shape? Okay, you're not gonna put that next lone pair right here, right? Because it'll be bumping uglies, or a lot of repulsion is happening. Instead, you're going to put it upstairs, and so what's left is your square planar arrangement, all right? And so now that you have square planar, we have 4 bonds that are all identical. So after that, it doesn't matter where you put the next lone pair, right? In any case, whether you choose any of the 4, you'll get T-shaped for any of them, all right? So 3 lone pairs, you get T-shaped. But now that we have T-shaped, if you want to put another lone pair on, where are you going to put it? So it's as far away from other lone pairs. Are you going to put it here? Are you going to put it there? No, you're not. You're going to put it here, over here. So all of the lone pairs are kind of in a plane. So they're as far away from one another as possible. And that's how you get the last shape here. If you have 2 bonds and 4 lone pairs, you get the linear shape, which is kind of funny. But there's actually no molecules that adopt this shape. So, but just, the thought experiment here, just theoretically, if you had 2 bonds, 4 lone pairs, it would make that shape. So just like our bent arrangement, remember how there's 2 ways to make a bent arrangement? There are 3 different ways to make a linear arrangement. And there's 2 different ways to make a T-shaped arrangement. All right, so do look into those, how you get those. It's differing amounts of lone pairs with differing, the same amount of bonds. So here, this T-shaped is 3 bonds, 3 lone pairs. But if we look at the T-shape that we did up here for our 5 electron domain template, 2 lone pairs, 3 bonds will also give us a T-shape. So that's a good question that kind of summarizes like comprehensively all of these different shapes if you really truly understand it. All right, how do we feel about all those? Good? All right. So the question is, do you have to memorize all these shapes? Yeah, kind of. Yes, you do. You do. How about the bond angles? Yes, you do. For the parent geometries, right? And then understand how to apply deviations. All right, so yes, you do need to know all these, know the names of the geometries, their bond angles, and the next part is, okay, let's determine overall molecule polarity. We talked about polar bonds last chapter, where we said, oh, if we had like a pretty large difference in electronegativity of the atoms involved in a bond, we called that a polar bond. We can measure that with a bond dipole or a dipole arrow. So the idea here that bond dipole is just created between 2 atoms, so 1 bond, but in a molecule we have many bonds that exist in space with certain bond angles. So if we think about those bond dipoles from chapter 8 as vectors, we can apply those vectors on the molecule given their bond angles. It's not that bad, okay? It's not vector math. I'm not good at vector math. So my strategy I use to determine if a molecule is polar or not is I use a system that I call babies versus bodybuilders. that I think about the atoms that make up a molecule, and I pretend that those atoms are pulling on the central atom at the certain bond angle. If, you know, two babies are 180 degrees from one another and they're both pulling on a toy at the same time, will the toy move if they're 180 degrees? No, they won't, right? What if the two babies were, what if it was bent? What if it was 120 degrees? If two babies are 120 degrees away from one another and pull on a toy, will the toy move? Yes, the toy will move. So that means the molecule is polar, okay? What if we had two bodybuilders pulling on a toy 180 degrees from one another? Will the toy move? No, assuming they're the same strength. Same strength bodybuilder. It'll cancel out, right? Their vectors cancel, so that molecule is non-polar. But what if we had a toy and there was a bodybuilder on one side and a baby on the other, and they both pulled on it at the same time? Okay, would the toy move? Yeah, so what kind of molecule is that? It'd be polar. So that's how I think about vectors, okay, instead of the math. So the idea here, okay, if the vectors cancel in 3 dimensions, meaning you have to apply Vesper theory, you have to apply the bond angles, then the molecule's overall nonpolar. Even if the bonds themselves are polar covalent. So for example, CO2, CO is a polar covalent bond. Right, both of those the carbon and the oxygen, see how there's 2 different bond dipoles, but they're pointing in opposite directions. So we have 2, I don't know, babies that are pulling on the molecule at the same time, but they cancel. So even though there's 2 polar covalent bonds present, because of how they're arranged, they cancel in 3 dimensions, so CO2 is a nonpolar molecule. So if the vectors don't cancel in space, then that molecule is polar. We're not going to do any like actual vector math. We'll just say, is the molecule polar or not polar? So the example here is water. Because of the arrangement of the bonds, both of those bond dipoles are not canceling in 3 dimensions. So we see that there's an overall net permanent dipole in one direction. So that's why water is a polar molecule. So the idea here is that both of these examples, both molecules technically contain polar covalent bonds. They both have bonds that have dipoles, but because of the arrangement of how they cancel out, only water is the polar one. Okay, so understanding, you know, do the vectors cancel out in 3 dimensions? If you use my babies and bodybuilders analogy, it will help you because things get confusing when lone pairs are involved. I like to just think of the lone pairs as bodybuilders, and then that works. All right, so let's think about it. All right, these are the molecules. Let's just determine, will the bond dipoles cancel in 3 dimensions? CO2. So I like to think of like the carbon atom as the toy or the tire or the thing that they're pulling on. And then we have 2 oxygens. Oxygens that are exactly the same electronegativity. So it's 2 babies that are exactly identical and they're pulling on the tire at the same time. The tire does not move. So that would make this a nonpolar molecule. Nonpolar. Do you see that? Okay. What if it wasn't CO2? What if it was carbon with a sulfur and an oxygen? What if it was that instead? Is that polar or nonpolar? What do we think? Polar, yeah, because are the babies the same strength pulling on the tire? No, they're not the same strength. So that means that the tire or whatever, the central atom will move in some direction. Doesn't matter where, what direction, it doesn't matter. It's just that it does move, so we do technically call that polar because the things that are pulling it on it are not the same. All right, BF3. So remember, you're applying Vesper theory, and so all of these Lewis structures, it's trying to show you what the shape is. So BF3, 3 electron domains, it's trigonal planar. What is that, polar or nonpolar? Nonpolar. Do you see babies in bodybuilders? Does that help? Yes, and you see all 3, they're all 120 degrees from one another, they pull on it at the same time. It cancels, so it's nonpolar. Okay, what about NO2 minus? So this is nitrite. Polar? Yes, because is it 3 babies pulling on it? No, it's 2 babies this way that are pulling on it, and then a lone pair. that's pulling on it 120 degrees away. So there's this unequal vectors that are adding up. Doesn't matter what they add up to. We just know that they don't cancel in 3 dimensions. So that is polar. Okay. So some of you might be thinking, well, if lone pairs are on my central atom, it'll always be polar. That's not quite true. Yeah, question. What? I'm answering it right now. Wow, I'm so good. Okay, let's just keep going. All right, CH4, polar or nonpolar? Nonpolar. This one's a little bit tricky because now we're no longer, just doing like linear, trigonal planar. Now we're doing tetrahedral. This is in 4 dimensions. So we still have like a tire, but we're pulling on it in 3 dimensions. So we have 4 babies all pulling on it, but in 3 dimensions. But because they're all 109.5, they all cancel, so it's nonpolar. What about ammonia? Polar, yeah, because it's still tetrahedral, but now we've replaced one of the babies with a bodybuilder, and so now it's polar. Yeah. It just works. It works. I don't know. Okay, what about water? Polar, yeah, because now we have 2 babies, 2 bodybuilders. Yeah, that will never cancel. Okay, let's keep going. So 5 electron domains. So trigonal bipyramid. This one's a little bit tricky. We have 5 babies. 3 of them are all 120 degrees from one another. So don't those cancel, the ones in the equatorial. Then we have 2 babies that are 180 degrees from one another. That's the axial. So do they cancel? Yeah, so what is this? Nonpolar. Very good. Very good. All right. What if we put a lone pair on it? Polar, yeah, because that lone pair, it's just going to mess up everything. Okay, it's pulling it to one side. All right, what if we have 2 lone pairs? Polar, yes, polar. And do note that we're putting those lone pairs in the right place. Okay, now this one, linear. Wow, you answered that so quick. Yeah, because describe what's pulling on our tire. We have 2 babies that are 180 degrees, they cancel. But then we have 3 bodybuilders that are all in the equatorial region, all 120 degrees, and they cancel. All right, so in this case, so here's the example where there are lone pairs, but it just so happens that they do cancel. So we need to be cognizant of those shapes. So this is nonpolar. That one's kind of tricky to see. Okay, all right, keep going. All right, octahedral. Nonpolar, yes. Square pyramid. Polar. Do we all see this? We all see it. They're just pulling on it differently. Okay. What about square planar? Nonpolar. Very good. So we have 2 bodybuilders that are 180. They cancel. And then the 4 cancel. All right. What's next? T-shaped? Oh, wait. No, they don't have it. Okay. Never mind. All right. That's good. All right. So let's look at some other examples here. Okay, so here is like carbon. Carbon always makes 4 bonds, so I just have a couple examples of, okay, CH4, we already said was nonpolar. Well, what if we replace one of those hydrogens with something else? So we want to be thinking babies and bodybuilders here as well, and I tried to show you the 3 dimensions going on here. So CH4, is this polar or nonpolar? Nonpolar, yes. But that's when all of the bonds are identical. So now the question is, well, what if they're not all identical? What if we replace one of those hydrogens with a fluorine? Is it polar or nonpolar? That would be polar because we replaced one of them, yes. Okay, what if we replaced 2 of them? It's still polar. Yeah, you can think, oh, I have 2 bodybuilders on one side pulling on it and 2 babies on the other side pulling on it. It's going to be nonpolar. And they're not canceling out in 3 dimensions. All right, what about if 3 of them are fluorines and 1 is hydrogen? Still polar, okay. And then finally here, what if all 4 of them are fluorines? This would be nonpolar. So the idea is, okay, if they're all 4 hydrogens, it's like 4 babies pulling on the tire. But if it's 4 fluorines, it's like 4 bodybuilders pulling on the tire. But in both scenarios, everything cancels. All the vectors cancel. But if ever there's like a mismatch, then they don't cancel. Good? All right. All right, let's do one more, okay? which are polar. This one's a little bit tougher, okay, because we don't have a central atom. So I'm telling you here that we have like a carbon-carbon double bond here. All of these molecules are flat, where all the bond angles are basically 120 degrees. So still think about the babies and bodybuilders analogy. And let's see if we can't figure out which ones are polar and which ones are nonpolar. So for me personally, I like to say more electronegativity is the polar stuff. So the idea for this first one is like the chlorine is the bodybuilder. So do you see this molecule moving in space if you apply the babies and bodybuilders? Is it moving? Yeah, because we have two like really big bond dipoles pulling this way, but then just two really small ones, small little babies pulling that way. So this molecule, does this cancel? No, so this would be a polar molecule. This one would be polar, all right? Versus, what about this one? Also polar, because we got two big hulking bodybuilders and then two tiny little babies going that way. All right, so this would be polar, that one, where the chlorines are on the same carbon. Okay, but what about this one? Wow, you guys are good. This one would be nonpolar. Do we see how this one's nonpolar? Okay, where the carbon-chlorine bond, that's basically the big, polar bond that we're worried about. There's our bodybuilder. So these actually cancel out in 3 dimensions because look at the bond angles. These are all 120 degrees from one another. So these two actually cancel each other out. And then same thing with the small bond dipoles that are created from the carbon-hydrogen. Those also cancel out. So this molecule is actually nonpolar. So that's a tricky one. And so this is an interesting example because if you look at the formula for all of these, all 3 of them, they have the same exact chemical formula. They are all what we call isomers. They're all 2 carbons, 2 hydrogens, 2 chlorines. But because of their structure, way different structure here, some of these we call like the cis version, the trans version. That's actually a different molecule. But regardless, different structure, way different properties. Some of them are polar, some of them are nonpolar. So that's important, okay? And you'll talk more about this cis-trans isomerization when you get to organic chemistry, right? So you'll see this again. You'll see this again. All right. All right. So how do we feel about polarity? Good. So you have to have a real good, strong grasp of molecular geometries, okay? And actually then I think applying the idea of bond dipoles to those actual shapes isn't that bad if you just think about, vectors, vector math, but I don't like to think about vector math. I just think of babies and bodybuilders. I had a student run into me in the hallway. They're taking organic now, and they said, I still think about babies and bodybuilders, and it helps me so much. So, and they're in organic now, and they're doing fine. So there we go. So keep that in the back of your mind to understand, is a molecule overall polar or nonpolar? So any questions? Did I answer your question? Yes, very good. All right, so that is molecular. So we did the first 3 parts here, shapes, okay, Vesper theory, and then applying the idea of bond dipoles to those shapes. Okay, so remember 6 steps to Lewis structures, memorize those tables, those electron geometries, and their bond angles. And then lastly, you can apply deviations to those bond angles just by understanding, electrons, when they're in lone pairs or double bonds, are just a little bit fatter. So now my favorite part of the chapter, and it's probably the hardest to explain, but I think I do a good job in it, is our advanced theories of chemical bonding. Advanced theories. So we're learning something advanced. All right, so we're using the concepts we learned previously. Because remember, when we think about forming a bond with Lewis structures, right? Like we have 2 hydrogen atoms. It forms a bond because they can share electrons. Those unpaired electrons they share, right? That's a covalent bond. That's what we say with Lewis structures. But the thing is, are electrons dots? No, they're not. In chapter 6, we learned that electrons are waves. We learned electrons, they exist. Does an electron orbit around a hydrogen atom? No, it exists in what? An orbital, all right? So that's what valence bond theory is. We're now recognizing that electrons are not dots on a page. They exist in orbitals, all right? Oh, okay, okay. Limitations of Vesper theory. Okay, so Vesper theory is really good. It's really good. at predicting shapes. Okay, it's really good at predicting shapes and all that, like polar, non-polar stuff. But there's stuff it can't do. It can't do everything. Even Lewis structures, it can't do everything, but it works. Our 6 steps, it works really well. But there's some things it can't do, and that's what these different theories are going to talk about. So Vesper theory does not describe multiple bonding, so we need to use valence bond theory to do that. And then these last things, Lewis structures and valence bond and Vesper theory don't predict magnetism and can't predict the stability of molecules, like whether they exist or not. And that's where we bring up MO theory, and that's the last advanced theory we'll talk about here. So we're going to talk about valence bond theory first, and it will hopefully clarify the idea of resonance also. So it's going to do a lot of things. So the whole idea is that electrons are not dots on a page. Electrons actually exist in orbitals. When we think about that electron on a hydrogen atom, what orbital is that electron in? S1, yeah, it's 1s1. What does a 1s1 orbital look like, or a 1s orbital look like? It's like a sphere, it's like a circle, all right? So in Lewis structures, we said that a covalent bond is formed when 2 unpaired electrons are shared. What valence bond theory says is basically the same thing, but we consider orbitals. We say a covalent bond is formed in valence bond theory when 2 electrons overlap their orbitals. More orbital overlap, stronger the covalent bond. So the idea here is like this. These pictures depict Lewis theory, where we have just the unpaired dots combining, but what valence bond theory says is, hey, no, these 2 hydrogen atoms, they're actually overlapping their orbitals, those circular orbitals, so they exist in the same space. So now we're just thinking about where those unpaired electrons are in terms of their orbitals, and we're bringing them close to one another in 3 dimensions. And so when those 2 spheres overlap, that overlap of the 2 spheres, like a Venn diagram, is what produces the covalent bond. So the idea here is that it's the space between here, all right? The electrons, that's the electron sharing. That's equivalent to like right here in our Lewis theory here. And so the more overlap that we get, the stronger the bond. So here, here's our like energy diagram. Here's just 2 hydrogen atoms just like hanging out apart. But as we start to bring them together, what we're doing is we're bringing together these 2 electron clouds, all right, from their orbitals, and that overlap of those 2 electrons, essentially you get double the attractions. Those electrons are now attracted to both nuclei. You get this stability. And so that is, here's our predicted bond length for a hydrogen atom. So like right here at this energy well is saying, hey, that hydrogen-hydrogen bond, that single bond, is stable, and we make a hydrogen-hydrogen molecule here, right? And so it's the overlap of those 2 electrons. We can say that they're in opposite spins. They share the same space, and it forms the bond. It might sound like Pauli's exclusion principle, because it is, right? We talked about Pauli's exclusion principle for atoms. It exists for molecules as well. All right, so let's talk about, let's draw the pictures. I think this helps with valence bond theory, because the idea is, okay, yes, electrons are no longer dots on the page. We can't just do this. We need to think, where are those electrons? We said that in a hydrogen atom, that electron is in a 1s orbital, right? So if we have 2 hydrogen atoms, we have 2 of these, right? We have one hydrogen atom where there's an electron in the 1s. There's another hydrogen atom with 1 electron in the 1s. All right, so what we're saying when we form the covalent bond is we overlap these 2 orbitals, and that's what this picture is trying to depict. A 1s orbital looks like this sphere. And so when we bring those together, the overlap of those 2 orbitals, we get the pairing of these 2 electrons, the sharing of those 2 electrons, except this electron is spinning the wrong way. Technically, we want it to be spin down. So when we bring those together into the same space, that we don't violate Pauli's exclusion principle. We see that? So bringing together 2 S orbitals, we get this head-on overlap, kind of like a Venn diagram here, and it's this overlap is what creates our covalent bond. That's in diatomic hydrogen. We can do it for other molecules as well. All right, so HCl, okay? So HCl, again, if we think about the Lewis structure, all right? When we think about HCl, don't these two electrons just share, the two unpaired? So again, think about where are those unpaired electrons? We already did it for a hydrogen atom. It's in that one electron right there is in an s orbital. And so we draw it as a sphere. What kind of orbital is this unpaired electron in? It's in a p orbital. Yeah, if you write out the whole electron configuration for chlorine, it's 3s2, 3p5, right? So p5, right? There's only 5 electrons in the p orbital, so there's 1 leftover electron. So let's just draw that. So it would look like this. I'll do this one spin down. So there, I have my 5 electrons in those p orbitals. So just like in the Lewis structure, we want those 2 electrons that are unpaired to share. Right, share, and that's how we make the covalent bond. So in this picture, I'm just showing the orbitals that I highlighted, that I have a electron in a 1s orbital, right, that's the sphere, and then I have an electron in a 3p orbital. What does a p orbital look like? Yeah, it looks like the dumbbell. So we have a dumbbell here. So if we bring the dumbbell and the sphere close together, can they overlap in space like our hydrogen example? Yes, they do. See, we have this Venn diagram like sharing of space. There's our covalent bond. That's what valence bond theory is saying, is we're bringing orbitals together, okay? They're sharing space. That's how we make the covalent bond. But the great thing is that these examples are consistent with the molecular shapes that we would predict. What is the molecular shape of diatomic hydrogen? It's kind of a trick question. It's not on your table, but 2 dots always, yeah, it's linear. There you go. 2 dots always make a line. All right, so it's just 2 atoms. It has to be linear. All right, so when we bring 2 spheres together, is that bond, the molecule that's being made, is that linear? Yes, it is. What about HCl? What's the shape of that? Also linear, yeah, it's 2 atoms again. When you bring 2, like a sphere and a dumbbell together, does that come together in a linear arrangement? Yes, it does. What about if we do chlorine-chlorine? Again, we want to think about where are the unpaired electrons, where do they exist? In these examples for diatomic chlorine, in what orbital is the unpaired electron? It's in the p subshell, again, because it's 2s2, 3p5. So for these 2 molecules, all right, or atoms, we have, there's our 3p5 on one chlorine, and then we have another one over here, all right? And so valence bond theory just says that these 2 electrons share space. Okay, we overlap those 2 electrons that happen to be in p orbitals. We overlap them in space. Do these 2 atoms make a linear arrangement? Yes, they do. All right, and so that's the beauty of valence bond theory. But in all of these examples where I have like diatomic hydrogen, diatomic chlorine, HCl, all of these are linear examples. All of these examples can use what we say atomic orbitals, right? Just s orbitals. P orbitals. We have a problem. We have a problem, and I'll talk about this in a little bit, is that you can't get all of the molecular shapes with just s and p orbitals. What other shapes are there? Other than, tetrahedral, trigonal planar, trigonal bipyramid, octahedral. Can you just use s and p orbitals and overlap them to get a trigonal planar? None of the orbitals, okay, like S and P, none of them exist in 120 degrees, so we have a problem. None of them exist in 109 degrees for tetrahedral, so we have a problem. So this is where the idea of hybridization comes into play, where sometimes we need to mix atomic orbitals to get new shapes that is consistent with Vesper theory. And the big idea for hybridization is right here, all right? Right here. Okay, based upon the number of electron domains around your atom, or your central atom, the number of electron domains, tells you the number of atomic orbitals you need to mix, and that will be the number of hybrid orbitals you get out. And I'll show it, it'll make more sense next week, but that's the big idea. So to get the shapes that we want, to make all the different molecular shapes, we have to mix different atomic orbitals. All right, so have a good weekend, everyone. Remember, chapter 8 homework is due this weekend.